is probably, I think we could probably have an hour-long discussion on this topic.
Really?
Unfortunately, then we would not get to hear our speaker. So since it's noon here in California, I'm going to go ahead and start this. So we're very pleased to have Nergis Mavalvala here as our speaker today for the VAMOS seminar. Nergis is the Curtis and Kathleen Marble Professor of Astrophysics at MIT, where she is also the Dean of Science, and so I'm actually amazed that she found time for us in her busy schedule. Nergis did her undergraduate studies in physics and astronomy at Wellesley and went on to pursue a PhD at MIT, where her work included sort of building the first early prototype of the LIGO gravitational wave detector. She went on to be a postdoctoral fellow at Caltech and has been on the physics faculty at MIT since 2002. And there she has become really established herself as a leader in efforts to push gravitational wave detectors towards fundamental quantum limits of precision. So that includes work on the generation and application of squeezed light and the use of radiation pressure to manipulate and cool macroscopic mirrors. Nergis has received numerous awards for her work, including the MacArthur Foundation Fellowship. She's a member of the National Academy of Sciences, and I won't list all of the prizes that Nergis has received as a member of the LIGO collaboration. But we're very fortunate to have her here with us today to talk about listening for gravitational waves above the quantum din.
So, thank you so much, Monica, and thank you, VAMOS organizers for having me here. So yes, I have foolishly stepped into the role of Dean of Science at MIT, but my favorite things to do are still the science I'm going to talk to you about. Today I'm going to tell you a story that unfolds in roughly three parts. The first part of my story is going to be a little bit about gravitational waves and gravitational wave detectors, because it sort of motivates much of the rest of the story I will tell you. And because gravitational wave detectors are involved, I have to really upfront recognize that many of the data that I will show you is really the fruits of the efforts of over 1,000 scientists who are part of the LIGO collaboration. The second part of my story will tell you about some of the quantum engineering that we have been doing to make improvements to LIGO. And then the third part of my story is going to take that to another level of how we can use some of these technologies we developed for LIGO in the service of quantum mechanics. So you can think of part two as quantum mechanics in the service of LIGO, and then part three as LIGO in the service of quantum mechanics. So let's get started. So all of you by now have seen this iconic graphic of the first gravitational wave signals ever detected by the two LIGO detectors in 2015. And these are sort of, this iconically defines the moment where gravitational wave astrophysics, the first detections were made, right? And there were first detections. Einstein's theory was proven, and in at least the time-dependent part, the wavy part. These were the first observations of binary black hole collisions. And then for someone like me who has spent my entire career thinking about how to design and build detectors that are sensitive enough, and in this case at the atometer scale of precision, this was also a real sort of highlight for the detectors. But if we want to really, birthing a field means more than making one detection. And so really what I want to do in this part of my talk is to sort of tell you about the opening of a new window into the universe, and not just that we made this first detection and put another check mark against general relativity, but everything that's happened since. And that's nicely captured in this graphic. So Advanced LIGO, which was the second phase of LIGO, began in 2015 and very quickly had that first detection. We've had 3 observing runs to date. The first observing run was the one in which LIGO made those first iconic discoveries. About a year later, there was a second observing run where LIGO's European partner observatory, Virgo, joined the run. And in the first observing run, we saw 3 black hole collisions. In the second observing run, we saw 7 more black hole collisions, and the very first collision of 2 neutron stars, so binary neutron stars. And in those 2 observing runs, we were seeing roughly about 1 event per month, 1 gravitational wave event per month. And that's what's shown in this graphic to the right, where observing run 1 and 2, you can see sort of the slope of the cumulative rate. And then there was a roughly year and a half shutdown, 2-year actually shutdown, and then we came back up with observing run 3, and in that observing run, you can see the observing rate has really skyrocketed, where we've gone from roughly 1 event per month to over 1 event per week. And so some of the story I want to tell you about today is how we did that. How did we change the slope of the detections there? And it's a beautifully quantum story, mostly, not entirely. So in observing runs 1 and 2, here were sort of the panoply of objects that were seen by gravitational wave detectors, LIGO initially, and then Virgo, when Virgo joined, with the neutron star detection being the one at the bottom right, the one with the very long time scale for the lighter neutron star. In observing run 3, we have seen many other very mysterious objects, and I like to put I've selected 2 out of the many that we've seen because they are very they're astrophysically interesting, and here I won't belabor them too much, other than to say that in making these observations of over 80 objects now, nature has really presented us with many astrophysical mysteries about how these black holes form. Why are they so massive? What are the mechanisms? There are many unanswered questions, and that really propels us to continually improve the detector so we can see objects that are either farther away or fainter, or both. And so indeed, to really launch this new era of gravitational wave astrophysics, we need to have detectors that have more sensitivity, more bandwidth, and more runtime. So let me quickly dissect for you the anatomy of a gravitational wave detector, so that we can then talk about how these detectors have gotten us to this new place of observing about an event per week. So the gravitational wave measurement really is measuring the change in distance at the level of 10 to the minus 18 or 19 meters. And that's done by using an interferometer with mirrors that are free to move to respond to the passing gravitational wave. So there are 2 parts to LIGO. There's the mechanical part, which is the mirrors themselves, and these are the glorious test particles of general relativity, if you will. So if you come at it from general relativity, you will see the mirrors of LIGO, or these test particles of general relativity, as the most beautiful object. If you come at LIGO from light, you will see the laser light as the most beautiful object. But either way, and today what I'm going to do is I'm going to convince you that the one without the other is pretty useless. So both are objects of beauty. So the mechanics in LIGO are that the typical mechanical motion of a mirror like of LIGO, they're typically of order kilograms. And if you just leave it this mirror sitting around in its natural environment, it would move by about a micron. So the first great challenge of LIGO is to isolate the mirrors from vibrations by a factor of a trillion, to get from a micron to 10 to the minus 18 meters. And that's typically done by using a series of vibration isolation techniques, including hanging the mirrors as pendulums, and typically with a resonant frequency of about half a hertz to a hertz. And this is important for the future parts of my talk. Now, the second part of LIGO is that once you have succeeded in achieving a mirror that's moving by less than 10 to the minus 18 meters in our measurement band at 100 hertz, you also need a way of measuring such a small displacement. And there comes the light. The laser light is our meter stick, if you will. And indeed, the wavelength of the laser light, which is a micron, is the tick mark on our ruler. And so there comes the second factor of a trillion, where to resolve motion of 10 to the minus 18 meters, we have to resolve an optical fringe by a factor of a trillion. And this is equivalent to saying we want to make a measurement that's 1 trillion times more precise than the spacing of the tick marks on our ruler. And the way we do that is by averaging over all the fluctuations of the light, and indeed by using a lot of laser power to reduce the shot noise or the light fluctuations. And in the operation of advanced LIGO, that typically translates into nearly a megawatt of laser power circulating in the arms of the interferometer. Now, when you do that and put it all together, you get curves like these. So on the horizontal axis is frequency, and on the vertical axis is the gravitational wave amplitude. Now, if you like to think about noise in terms of displacement noise, you just take this vertical axis and multiply it by the length of the detector, which in the case of LIGO is 4,000. And I'll go interchangeably between those two. These curves show the sensitivity of the different phases of LIGO. The first phase of LIGO, called initial LIGO, was completed in 2010, and that's the green curve. The red curves were the advanced LIGO detectors during observing run 1 when the first discoveries were made. And then the blue and cyan curves are the ultimate target design of advanced LIGO. And the cyan curve is actually an upgrade that we're already designing and planning for, which I will say quite a bit more about later. One of the big changes in going from the green curve to the red curve to the blue curve is the amount of input laser power we use, going from 10 watts to 25 watts and eventually to 200 watts of input laser power. And that is all in the service of reducing the shot noise, which scales as the square root of the power. Now, to understand how to do better, we have to kind of look a little bit at the noise sources in LIGO. So let me really just quickly walk you through this. It's a busy plot. I don't want you to pay much attention to very much in this plot, other than the black curve is the advanced LIGO design sensitivity. And the magenta curve that's just below it is the total quantum noise in LIGO. So the takeaway, and then the next closest sort of noise source that troubles us is the red curve, which is the Brownian thermal noise of the mirror coatings in LIGO. And what you see is that the magenta curve more or less dominates the sensitivity limitations of advanced LIGO. And we tend to think of these in two parts, even though they're really part of the same quantum fluctuations. At high frequencies, the instrument is limited by shot noise. This is literally our inability to resolve the phase shift of light because of the quantum fluctuations on the light. And this is a case where putting in more laser power would help. It brings that curve down and it gives us a stronger measurement. But in quantum mechanics, we also pay a price for the stronger measurement, and that is that we get stronger back action. And that is on the low frequency part of the curve, we're limited by the radiation pressure noise. And what this is simply the fact that the photons that we use to probe the position of the mirror carry momentum. And the quantum fluctuations in the number of photons give us fluctuating momentum kicks to the mirrors. So this is a classic problem in quantum measurement where the process of making the measurement actually disturbs the measurement. And it's fundamental. It's not like you could make a more perfect measurement and you would do better. Although in a few minutes, I will tell you that whilst you can never violate this manifestation of Heisenberg's uncertainty principle, we can certainly manipulate it, and we will shamelessly. So that sets up for us what limits LIGO. It's quantum noise. If we want to do better, what must we do? So I'm going to take a short pause here to see if there are any questions on part 1, which was setting up the problem. And the next part will be the quantum engineering we do to make a dent and to improve the sensitivity. So brief pause.
Actually, I have one quick question. Can you say a little bit about how the shape of that curve depends on the line width of the cavities in LIGO, and whether that's sort of a free parameter that one might change? Or
yeah, so that's a good question, Monica. So let me just say a little bit about that. Shot noise, as we know it, is flat, right? It's a white noise source. So the fact that the LIGO curve goes up at frequencies right here, say above above about 200 hertz, it starts to go up, and it goes up as literally as a function of frequency, to the first power of f. That is defined by the line width of the LIGO cavities. That basically sets the storage time of the photons in the instrument. The low frequency part where is falling typically as 1 over f squared, and that is simply coming from the susceptibility of these mirrors that are hanging as pendulums. So the mechanical susceptibility of the motion of the, converting a force to motion of the mirror. So those are the two big frequency dependent parts of this quantum noise. 1 over f squared from the susceptibility to force of the mirror, so that's a mechanical effect, and then the f to the first power above the cavity pole. So, good.
So then we have a question from John Simon, who asks, is there a possibility of using the crystalline coatings that have been adopted in clock experiments to reduce coding Brownian noise?
Absolutely, yes. And the big challenge there is actually more of a sort of a technology development challenge, which is scaling up these crystalline coatings, aluminum gallium arsenide in particular, or coatings, to the size that's needed for LIGO, which has a 35 centimeter diameter aperture. So that's really the challenge. These have been hugely successful at sort of the, sort of the inch and 2-inch scale, but scaling up to 35 inches with that level of purity and uniformity remains an unsolved problem.
Thanks. And we'll just ask one more question here from Bill Phillips. The improvement in event rate or range of reach is an obvious advantage, but what about better signal to noise for the nearer events?
Absolutely. So that is certainly part of it. And in fact, we regularly do exercises of asking, Bill, asking ourselves, if we had this sensitivity when that event happened, what kind of SNR might we have gotten, and what might we have seen astrophysically that we couldn't? So that is totally, absolutely part of the goals here.
Great. Okay, so with that, I will just remind all of our listeners that you can type your questions into the Q&A or the YouTube chat, and for now, I will let you continue, Nergis.
Wonderful, thank you, Monica. So part 2 is quantum engineering, and in particular, the quantum trick that we use is to inject squeezed states of light into our interferometer. So let me introduce that, and this may be one of the more important pedagogical moments in my talk. So the idea of using squeezed states of light, to really use them fruitfully, we have to understand where the quantum noise in the interferometer comes from. And to do so, I'm going to walk you through this very toy interferometer. It's a Michelson interferometer with a laser at one port, and we arrange the path lengths to be so equal that there's perfect constructive interference, and all of the light goes back towards the laser. And what that would say is, by conservation of energy, that none of the light comes out at the output port. And that classically, that's roughly the configuration in which LIGO works. And that's oftentimes why people refer to the output port where the signal comes as the dark port, because it's just been arranged to be dark. Now, quantum mechanically, this description is inadequate. It actually violates both energy conservation and commutation laws. Quantum mechanically, when you have a quantum system with an open port, you must introduce their quantum vacuum state. So the first thing that, and you can see this also conceptually, which is that indeed in this classical description, if all the light was going back towards the laser, then all the noise that comes on the laser should also go back towards the laser. And here at this output, at the dark port, you should be able to make a noise-free measurement. And we know that's not possible, again, violative of quantum mechanics. So the first pedagogical construct I want to set up is that at this output port, in comes a quantum vacuum state. And you can see it's depicted in space here in quadrature phase space as a circle centered around the origin. Now, by the symmetry of the beam splitter, for the same reason that the laser light goes back to the laser, the vacuum state that entered the output port will come back to the output port. So here it comes out to the output port, but now superposed on this vacuum state is a coherent state, and this is a small coherent state that's due to any gravitational wave that went by and created some light to come out this dark port. And the projection of this phasor, the classical phasor of our light, onto the noise circle of the vacuum state is the origin of the shot noise. That is what gives us the shot noise in the interferometer. And so it is the superposition of the coherent signal field with the quantum fluctuations. And this gives us a phase noise, if you will. Now, this same vacuum state also arrives at our mirrors inside the interferometer and also superposes with the intense light field that's hitting the mirrors. And it's that superposition that gives us the radiation pressure. It's the coherent intergravity field plus these quantum fluctuations, and that gives us the fluctuating radiation pressure force, which in turn turns into mirror displacement. So the vacuum state that enters the interferometer is the problem. And that's a very powerful thing to know, because then we can think about what to do. And so indeed, if you could inject, instead of a vacuum state, if you could inject a squeezed vacuum state depicted here in phase space with an ellipse where one quadrature is squeezed at the expense of greater noise in the other quadrature, then at the output, you can see that you could have a measurement where your signal, the yellow phasor, projects onto onto the small part of the noise ellipse, and you can make a measurement that has better signal to noise than if you had a vacuum state there, with one very important quantum mechanical caveat, which is that as long as you only measure along your signal phasor, you have an improved measurement, but any measurement that goes in the orthogonal direction will pick up this extra noise that you've manipulated into the other quadrature. This idea was brought to us by Carl Caves, and it was brought to us actually as early as 1981, where he says the key requirement of the squeeze state technique is that the state of light entering the interferometer's normally unused input port must not be the vacuum state, but rather a squeezed state. Okay, so the idea has been around for a while. The implementation has taken a long time to perfect, and we're far from perfection yet, but to get to the place where it's useful. So fast forward now to last year, and this is after more than a decade of development of squeeze light sources that I won't talk about. We have a squeezed vacuum state that we are able to inject into the interferometer. So this busy graphic here on the left is the interferometer, and on the upper right is the whole readout chain for the gravitational wave signal, which happens far out at the right end here. And what we have done is we have come along with a squeezed vacuum source where we take the input state, to the vacuum, where we take the state of the vacuum state that would enter the open port, and we squeeze it. You can see these orange arrows depict the squeeze state being injected through a Faraday rotator. And much more, obvious than this busy plot of the experiment is the result, which is shown in the noise spectra on the right. The black curve is the advanced LIGO sensitivity during, just before observing run 3, when you have no squeezing. And then the green curve is what we have when we inject squeeze states, and that has amounted to a roughly 3-ish dB factor of improvement, or square root of 2 improvement in signal to noise ratio, 3.2 dB. Also shown on this plot, and this is not important for the measurement now, but it will be for some measurements I show later, the magenta curve is our model of the quantum noise. And when you subtract the magenta curve from the black curve, that gives you the gray curve, which is all of the quantum noises. So all of the classical noises in the measurement are given by the gray curve, and you can see that the instrument, above, certainly above 100 hertz starts to be completely dominated by the quantum noise for the most part. Now, notice something very important that is very technical, so I'll only measure it here. The angle of the squeeze state that we inject is 7 degrees. And the important thing to know is if we were trying to suppress shot noise, that angle would have been 0 degrees. Now, why do we need this little offset, a little rotation of our squeezing ellipse? We need a little rotation of our squeezing ellipse because that's the angle that gives us the best sensitivity to gravitational waves, which is in the bucket of the curves. And what is going on there is best seen in this curve here, which is, again, blue is without squeezing, red is with squeezing. And now I draw your attention to this low frequency part here, where the red curve goes above the blue curve. And indeed, so when we make an improvement in the shot noise, that is the narrowest part of the ellipse being sampled here at the higher frequencies. But now the wide part of our squeezing ellipse is disturbing the measurement. This is the quantum radiation pressure starting to disturb the measurement. We have enough power in Advanced LIGO now that the quantum radiation pressure noise is a problem. And that's why we have to do that little rotation. And we'll come back to this theme in a moment. Again, Carl Kayes warned us this would happen back in 1980. He said there has been a controversy whether quantum mechanical radiation pressure fluctuations disturb this measurement. This letter resolves the controversy. They do. And indeed, that's what we're seeing in that increased noise at low frequencies. So now for the third part of my talk, I'm going to take again a little pause because I'm going to launch into radiation pressure, and I'm really going to try to convince you that it is not just a terrible scourge as Carl Kayes' 1980 paper warned us of, but it can be a force for good. So let me pause here and see if there are any questions on this part, which will tie back into the third part. So it's not finished, but here's a good place to pause.
Great. So we have a question from Brandon Smith, who asks, I am wondering why the squeeze state doesn't completely degrade for the N passes inside the Fabry-Perot arms. Each interaction with the mirror should mix some vacuum noise into the squeeze state.
Yeah, you are correct, but again, these are high finesse cavities. They have low losses, and indeed, so the quantum vacuum is leaking into the interferometer, but not at as high a rate as the squeeze state that we're injecting. So if you had a worse cavity, you're completely right. Eventually, you would just lose all your squeezing.
Okay, and then let's see, we have a question from John Kunjaman, who asks, in the current scheme, is there an optimal amount of squeezing and can you achieve this?
Yeah, so that's a very good question. And John, I will ask you to give me another 10 minutes to get to that if you'll be patient with me, because we'll tie this back to optimal squeezing.
Okay, great. I think there are some other questions, but I think at this point I want to let you keep going and we may hold some of these till the end.
Okay, wonderful. So thank you. So I already said, look, let's not just think of radiation pressure as this terrible problem. Let's also think of it as a force for good. So to set up this issue, this advantage that radiation pressure can provide for us, let me introduce the idea of an optomechanical cavity, which abound in LIGO. Remember, LIGO, it's filled with systems where you have an optical cavity, two mirrors facing each other, and you have movable mirrors, and that makes an optomechanical system as described here. So the movable mirror, oscillator interacts with this intracavity optical field. Now the light inside the cavity has a Lorentzian profile. It's a resonance because there's a constructive interference between the light that you're injecting into the cavity and the light that's circulating there. And that resonant phenomenon gives us a Lorentzian curve. So this is a figure that shows the power inside the cavity as a function of cavity length or detuning relative to the laser frequency. And of course, the power inside the cavity can be also is directly proportional to any radiation pressure force. The radiation pressure force is proportional to the power. Now, if you take this Lorentzian, this resonance, and if you detune yourself, they say you go halfway down the resonance to the part where you have a linear dependence on the cavity length, then you can create a radiation pressure force that's proportional to length. And indeed, that's what we can do. So when you blue detune, you can think of it as the following. You have a cavity, and if you pull the mirror to make the cavity slightly longer, the radiation pressure force goes down because there's less power in the cavity. And as a result, the radiation pressure uh, 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 force decreases and the mirror gets pulled back in. That's a restoring force. And now, because of the delay time in the cavity, the fact that the light has some finite storage time and it takes time to respond to the mirror motion, you also get an imaginary part that looks like a damping term. And so you have now light inside the cavity and detuning to either the blue or red side. So, at wavelengths higher than the laser frequency or lower, you have a complete set of knobs on applying restoring forces or anti-restoring forces, damping forces, and anti-damping forces. Damping forces are ones that give you exponential decay. Anti-damping forces are ones that give you exponential growth. And in our sign convention, these are the forces that are shown. And so now you're equipped with radiation pressure as a lever for creating forces and creating them in whatever, for whatever effects you are desirous of making. And this optomechanical coupling can be used for a variety of things. I'm going to give you a whirlwind tour of 4 measurements that we are able to make with this phenomenon. So we can shape the noise curves of LIGO using optomechanical coupling, using this radiation pressure. We can use this to optically trap and cool mirrors. We can use this to generate squeeze states of light. And we can also use this to create quantum correlations between the light and the mirror itself. And so let me then just take you on the tour. The first thing I'm going to show you is how we can use this optomechanical tool to shape the curves of advanced LIGO. And the green curve in this plot is advanced LIGO. And then all of the other curves are various ways in which you can use the radiation pressure to create an optical spring. So the restoring force that I just talked about, we call it an optical spring. And in fact, if you look at the dips on the left in these sets, in this family of curves, they are precisely due to the optical spring effect when we detune the readout cavities in advanced LIGO. Now, in reality, so you can say this is a tremendously advantageous thing, because what you can do is if you had a source that you wanted to measure with very high signal to noise ratio, of course, at the expense of sources at other frequencies, because you see these curves go above the green curve at other frequencies, you could do this. In reality, we don't do this because the thermal noise in advanced LIGO at the moment is high enough that it masks any of these dips that we could make. Now, there's one other curve I want to introduce on this plot, and that's the black curve. This black curve we call the standard quantum limit, and it is basically the balance between the radiation pressure noise and the shot noise at any given power. So I've told you, if you increase the power, sure, you bring your shot noise down, but you make your radiation pressure noise worse. And so this curve is the locus of all shot noise radiation pressure noise curves for different powers. It's not really a standard, because different fields have different standard quantum limits. It's also not really a limit, as you will see. It's really a benchmark, but it will play an important role in some of the stories I will tell you next. And what you can see is that this optomechanical coupling, the optical spring effect that I showed you at these resonances, actually allows you to go below the standard quantum limit. And that's why I'm not so fond of calling it a limit. But there we go. Now, the next thing I want to tell you about is optical trapping and cooling of mirrors. And so I'll start my story with a measurement that we made in my group back in 2006, where we took a 1 gram mirror. We suspended it from a pendulum just like the LIGO mirrors are, but we were trying to mimic LIGO, but instead of having 40 kilogram mirrors with a megawatt of light, we tried to do an experiment with a 1 gram mirror and few 10 kilowatts of light to get this effect. And then we shone two different colors of light into this cavity. We had one beam was blue detuned to create an optical spring, and that's the restoring force to trap the mirror. And then we used a red detuned beam to create a damping force and to cool the mirror down, to damp it. And when we did that, this is the measurement that we made. Let me just go quickly to the measurement. On the left side is the susceptibility of the mechanical oscillator of the mirror. And the different colored curves show different levels of optical spring frequency. So, this it's basically the frequency of the trap. Now, one thing that you'll notice is that all of the curves on the left side have a phase shift that increases through resonance. And in our convention, that's an unstable spring. And that was the optical restoring force, but an anti-damping force. And then we turned on the red detuned field to create an optical damping force. And you can see that the magenta curve is stable. And by using these different trapping and cooling optical forces, we were able to show that this mirror oscillator in this longitudinal mode of oscillation, which is along the cavity axis, which starts off sitting at room temperature, and then by optically cooling it, we could cool it down to an effective temperature of just under a Kelvin. This is a pure optical trap for the mirror. And that set off this a series of experiments one can do to apply this to increasingly larger objects, with the goal eventually of taking truly macroscopic human scale objects and being able to prepare them in interesting quantum states, including a quantum ground state. So now I'm going to show you a measurement that's really literally came onto the archive last night. This is an experiment in Advanced LIGO led by my colleague Vivek Sudhir and our graduate students Chris Whittle and Evan Hall as a postdoc in our group, and many others, but I'll call them out because they sort of led this experiment. And what this is it's the LIGO instrument. It has these mirrors suspended from pendula, as I've described before. And then we take this extremely sensitive readout, the gravitational wave readout. Now, remember, we have squeeze states being injected in. And we take this readout and we use a feedback loop to cold damp the LIGO mirrors. And the interesting thing, in the interest of time, I'll jump to sort of the result. On the left, you see again the susceptibility of the mirror. So these measurements are made at different trapping and for different damping levels that are applied. So let me just actually point out here how the damping works. So here we make this optical measurement, and we take the susceptibility that we imply from the optical measurement, and we can turn it into an effective susceptibility that has an effective trap frequency omega squared and an effective damping term gamma effective as well. And by varying gamma effective, the next thing I should tell you is the normal mechanical resonant frequency of this oscillator, this pendulum, is 0.4 hertz. And what we do is we take the optical spring and we optically spring it up with the optical trap to the place where Advanced LIGO has its minimum noise. and that's around 150 hertz. So in this band. So we take this mechanical oscillator, we couple it so strongly to the optical field that its mechanical restoring force is unimportant relative to the optical one. And then we put its, so that's the trapping frequency. And then we vary the damping, and that's the data shown on the right. And what you see is that for the greatest damping we could achieve, which is at the limit of the imprecision of the measurement, including the squeezing, that corresponds to a phonon number of 10. So this is a 10 kilogram reduced mass oscillator, which has 10 h bar omega of energy in it. So not quite yet at the quantum ground state, but we're slowly getting there by using the power of the radiation pressure forces to optically trap and cool the mirrors. Now, again, the next sort of exciting thing that we can do with radiation pressure is we can use it to generate optomechanical or ponderomotively squeezed light. And the idea here is that a squeeze state, it can be described as a state in which you correlate the amplitude and phase fluctuations of the light, whereas in a coherent state they're uncorrelated. In a squeeze state, you correlate them. So you can think of an optomechanical system like this. You start off with a coherent state. The amplitude fluctuations, or the number of photon fluctuations, applies a force on the movable mirror. The mirror moves, and when it moves, that motion changes the phase of the light, and the phase of the light then becomes coupled to the amplitude of the light, because the amplitude fluctuations move the mirror motion affects the phase of the light. And you can create a squeeze state in that way by creating this phase space shear of the optical state. And so here is an experiment we did with a slightly different mechanical oscillator. In this case, it is in collaboration with Thomas Corbett's group at Louisiana State University. And this was an experiment led by then graduate student in my group, Nancy Agarwal, where we take a small micromechanical, so this is a few hundred nanogram gallium arsenide Bragg reflector. And we do the same optomechanical tricks. We put it in a cavity, and then we measure the optical readout at the output. And what we find is that we can generate ponderomotive or optomechanical squeezing. So this plot on the right, as a function of frequency, shows the total noise relative to shot noise. So the flat black line and the data shown in blue are the shot noise limit, and then any where the noise goes below that, that is our squeeze state. And we show that we can make a broadband squeeze state at these frequencies using this optomechanical squeezing. And then comes the next very amazing part of what we can do with the radiation pressure noise, and that is we can actually use the radiation pressure to create quantum correlations between the mirrors, the 40 kilogram mirrors of Advanced LIGO, and the quadratures of the light. And so just as a reminder, I introduced the standard quantum limit, but let me just make sure we're all on the same page. So we all know that repeated measurements of position are imprecise. This is the back action, and it comes from the fact that our measurement is the position is measured by looking at the number of photons we measure. Those fluctuate because of the shot noise. And then there's the momentum kicks that give us the back action noise, also known as the quantum radiation pressure noise. Now, if the shot noise and the quantum radiation pressure are uncorrelated, their balance gives us the standard quantum limit. That's the thing that I introduced. Now, I also told you that you can circumvent it. And you can circumvent it by creating correlations between the shot noise and the radiation pressure noise quadratures. And the way that we can do that in Advanced LIGO is by using the ponderomotive squeezing that is occurring in the interferometer to create the correlation. So now I told you in part one, we make squeeze states of light and inject them in the interferometer. In the very last part, I told you we can use radiation pressure to make ponderomotive squeezing, and I showed you a laboratory experiment where that was done. There is also ponderomotive squeezing happening in the LIGO interferometer. And so now this next measurement is combining the two, the injected squeezing and the ponderomotive squeezing, combining them together. We can show that you can actually make a measurement that goes below the standard quantum limit. So here is the experiment. Again, this is done in LIGO. We have our squeeze light source, and the result is on the right. And so let me walk you through this. It's a busy plot, but I'll cut to the result first, and then I'll back up and tell you a little bit more about it. So the dashed red curve, the dark dashed red curve is the standard quantum limit. The dashed light red curve is 3 dB below the standard quantum limit. The black curve is what we start with in advanced LIGO if you have no squeezing. And the blue curve is the quantum noise model that we have. And these two curves I've introduced to you before. When you subtract the blue curve from the black curve, you get all of the non-quantum noises. And then when you inject squeezing, and you inject squeezing where the squeeze state is rotated to a quadrature where it is then further sheared by the ponderomotive squeezing, you get the green curve, which is the noise in advanced LIGO, showing that it goes below the standard quantum limit if you can arrange your injected squeeze state to be sheared by the ponderomotive squeezing in the interferometer. Now, I told you a little while earlier that we can't really use these correlations in the interferometer because the thermal noise is too large. And in reality, that is true. Here, we've made this measurement by subtracting out the thermal noise. And we know how to subtract out the thermal noise because we are able to measure the curve without squeezing, subtract out the quantum noise model, and all the remaining noise are the other noises. And in the Q&A, I'm happy to show you more details. But here, I wanted to just highlight that we are able to make a measurement. And the fact that we can go below the standard quantum limit tells us that we must have these quantum correlations, because without those, we don't know how to go below the standard quantum limit. So this is a measurement of correlations between light and 40 kilogram mirrors as manifested in this below SQL measurement. All right. The last part of my quantum story is the part that I think John asked the question earlier, optimum squeezing. So by now you've gotten a recurring theme, that is that the shot noise improvements occur at high frequencies, and the radiation pressure noise detracts from the instrument at lower frequencies. So the blue curve is advanced LIGO with no squeezing, and the red curve is if we injected 6 dB of squeezing as comes out of the squeezers that we're using in observing run 3, for example, right now. And you can see that as promised, the shot noise gets better, but the radiation pressure noise would get worse. Now, the reason it does that is that at high frequencies, the projection of the signal is along this narrow part of the ellipse. But at low frequencies, that same projection is now along the noisiest part of the ellipse. And everything else in between happens at intermediate frequencies. So if we could create a squeeze state that we could rotate as a function of frequency from horizontal, so phase quadrature squeezing to intermediate, and by low frequencies to amplitude quadrature squeezing, then we could get broadband improvement. And that is indeed what we are now doing. So we have an experiment where we take a squeeze state and we reflect it off a very, very high finesse optical cavity. Now, one of the things that us VAMOsers are very used to thinking about is that the optical cavity has this amplitude response, but it also has a phase response that's associated with the resonance. And this phase shift is a rotation in quadrature space. So when we take our squeeze state and we take a squeeze state that's not dependent on frequency, which is this input here. We pass it through this high finesse cavity. At the output, we get a squeeze state whose squeezing orientation is rotated as a function of frequency, and it's rotated as a function of the frequency as given by the line width of the cavity. And so we did a demonstration of an experiment in our labs at MIT. This work was led by Eric Olker in collaboration with my colleague Matt Evans. And we showed that you can do this frequency dependent rotation, which is given by the locus of all these curves, which is the black line. And you can see the squeezing ellipse being rotated as a function of frequency. And that would be the optimum. That would give us broadband squeezing. So when we do all of this, we come back to a curve I've shown you earlier. And that is indeed what this cyan curve was. At the time earlier, I just called it an upgrade, and I didn't tell you what it was. Now I can tell you what it is. It is the combination of injecting frequency-dependent squeezing that can give us a broadband improvement. And that is the next upgrade that we are ferociously installing and getting ready to do in LIGO. It is called A+ for Advanced LIGO+. And this is the sort of the nominal plan. So here's a whole set of curves that you're now used to seeing. The thing that I will just point out to you is that, you know, the blue curve was observing run 2. The orange curves are observing run 3 at different snapshots in time with and without squeezing. These are curves I've shown you. The green curve is the advanced LIGO design, which we're not yet at, because even though we have squeezing, we don't yet have advanced LIGO running at full optical power. We are still we're still roughly a factor of 2.5 more power to go. And then A+ is what we expect with the frequency dependent squeezing and one other technology to reduce the thermal noise, which is to have lower loss optical coatings that I'm not going to have time to talk about. So that's what the future brings. Now, beyond these upgrades to the 4-kilometer long LIGO and Virgo detectors, Virgo also has its own version of enhancements. The design for a next generation of detectors is already well along. And these are, for the first time in 30 years, going to turn another knob that we haven't been able to turn before. And we must turn because we are sort of at the point of diminishing returns with 4-kilometer long detectors, which is to turn the knob of length. So there's a program in Europe called the Einstein telescope. That's a 10-kilometer long detector. In the US. There we're looking at a 40-kilometer long design called Cosmic Explorer. This is this is being led by Matt Evans at MIT. Now, regardless of what you think of for future detectors, whether it's A+, 4 kilometers, 10 kilometers, 40 kilometers, the quantum technologies that I have described are here to stay. In none of these can we achieve any improvements without these quantum technologies. And then the other part of it is we have to also look at the novel mirror coatings, and in particular, as was pointed out earlier, you know, crystalline coatings. But when you do that, here is a series of curves, starting with the advanced LIGO design curve being the white curve. A+ is the blue curve. There is an intermediate 4-kilometer design called Voyager, but then eventually you get to these longer detectors that are Cosmic Explorer and the Einstein telescope that have another order of magnitude improvement in sensitivity. Now, astrophysically, there's something really remarkable about these 10 to 40-kilometer long detectors, which is that these detectors will be able to measure binary black holes of the typical masses that we're seeing, tens of solar masses, 10 to 30, out to a redshift of 10. And astrophysically, this is incredibly amazing because we believe that the very first stars formed at a redshift of 10. So when you can see to a redshift of 10 and beyond, you would be able to map out all binary black holes in the universe of those stellar mass black holes. And to me, this is kind of a remarkable thing that we could go from the first discoveries in 2015 to, in the time scale of the next 20-ish years, if we are successful in building these next generation of detectors, then we're going to be able to map out every black hole binary through in gravitational wave universe. So let me close my my talk with some closing remarks. So I think we have a really brilliantly dark and very warped future ahead of us. I've shown you that advanced LIGO's observing run with 3 with squeezing has been a success. Our rate of detections has really gone up. Our sensitivity has too. The A plus upgrade, will include frequency dependent squeezing and hopefully better mirror coatings. The planning for this next generation of detectors is well along the way. And something I didn't have time for, but happy to answer in Q&A, is we have a space-based observatory, LISA, which also is readying. And now let me finish with the sort of the single most important thing that I could tell you. This is the cast of characters. We have collaborations with our Thomas Corbett's group at LSU, and then an incredible number of super talented students, postdocs, and colleagues here. And I'll single out a few people. Maggie Say was the grad student who led the squeezing on advanced LIGO with How to New. How to New led the measurement of the quantum correlations. Vivek Sudhir and Chris Whittle and Evan Hall. These 3 guys led the measurement of the cooling to the 10 quanta above the motional ground state. So I don't have time to name each and every person, but these have been an amazing cast of characters to work with. So thank you for your attention. I'm actually going to stop my screen share. And then we can open up to questions.
Great. So thank you for a wonderful talk. We have a number of questions. I'll ask some subset of them. So Dima Budker asked, when you were showing sensitivity plots, he asked, could you kindly discuss the origins of the big spikes in your sensitivity plots?
Okay, so I'm glad I didn't stop screen share because it's probably easiest done by just pointing out. So let me start with the advanced LIGO plot. So I'll just actually I'll go to this one here. It's easier to see. So yes, so I would say every one of these peaks is understood. Some of them we wish would go away, and some of them are self-inflicted. So the first things you'll recognize are power lines, the 60 hertz, the 120, 180. The other things that are there is there's this family of resonances right around 340 hertz. These are the guitar string resonant modes of the tensioned fibers from which the LIGO mirrors hang. And so it's essentially the mode you would get if you twanged the fiber, and you might say, well, why are you twanging the fiber, silly? But we aren't. This is the thermal noise driving those modes. And then a number of these modes at higher frequencies are actually calibration lines that we inject to keep our calibrations current. And they loom large in these spectra, but they're extremely narrow, and they require us to remove a tiny fraction of the data. So they're not problematic. They're actually mostly good friends.
Great. So we have a question from John Simon, who asks, just for fun, how close are you to being limited by gravitational wave noise in your ability to cool the mirror to its ground state?
Yeah, so that's a great question. So gravitational wave noise, if you think of it as some broadband stochastic noise, there are 2 versions we have to worry about. The one is a version that is far below any sensitivity that we have right now, and that is, the primordial gravitational wave background, the gravitational wave analog to the cosmic microwave background. And in the LIGO band for sort of the standard, slow roll theories of inflation, that's something like, 5 orders of magnitude below our current sensitivity. So we don't worry about that. And then the other kind of noise we would worry about that would, would be a incoherent superposition of all the binaries going off. So, these are indeed spectrally point sources, but you have enough of them and you just sort of, flood your spectrum with white noise. And again, we're very far from that at a detection rate of a few per week, a few per month. And so there is certainly lots of people have thought about what happens when we get to that background limit. And in fact, one of the limiting noise sources for the Space Observatory, Lisa, will be this incoherent sum of all white dwarf binaries just going off everywhere in the universe. But LIGO, we're okay with that for many years still.
Great. So I'll just ask one last question. How many of these, sorry, this is a question from Joseph McGowan, who asks, how many of these challenges extend to mirrors for space-based interferometers?
Yeah, so it's a good question. So, the space-based interferometers are very quite different than anything we do in the terrestrial ones. So in the space-based interferometers, you start off with a few watts of laser power, and by the time you travel the 5 million kilometers and the diffraction limited number of photons you pick up is a few. So we work in the regime of having a very large amount of laser power on our detectors, and the space detectors are in the opposite regime. And in fact, because the space detectors are million kilometer long instruments, their displacement sensitivity is picometer. So, factor of a million less sensitive in displacement than LIGO has to be, for example. So you don't need these extreme tricks of getting to resolving a fringe to a part in a trillion, etc. So, and that's a damn good thing, because doing all of this in space is really hard.
Well, on that note, let's thank Nergis one more time for a really wonderful talk.
Thank you all for coming.
And I'm just going to say, so there were more questions, and there's a link that has been placed into the chat where people will be able to informally ask you those. But before we do that, if you allow me to just share my screen for a moment, I would like to advertise the upcoming talks. So next, can you see this?
Yes.
Yeah, great. Fantastic. So next week's VAMOS talk will be by Natalie de Leon from Princeton. She'll be talking about correlating materials analysis with qubit measurements to systematically eliminate sources of noise. And our sister series, the Quantum Science Seminar, next Thursday will be given by Florian Schreck on continuous wave BECs and super radiant clocks. So join us next week, and for now, join us in the post-seminar discussion room at the link. Thanks again.